So, in the last lecture, right, we studied the efficient realizations for decimation and interpolation filters. We saw what advantage we get in terms of computational complexity and you know the multipliers are not really resting, right, and we did this for an integer decimation rate, an integer expansion rate considering m equals 2, L equals 2. We also discussed how certain properties on FIR filters, I mean if we assume that the FIR filter has a symmetric impulse response, how that would affect the polyphase components, and we got a basic feel about some interesting properties with the polyphase filters, how those and we thought how we can incorporate these aspects into efficient realization. One is using efficient structures themselves for realizing decimation interpolation filters. Second is some additional properties on the base filter itself, how we can bring that factor also into efficient realization. So, suppose we want fractional sampling rates, and let us assume that we want an m by L decimation, right. So, we want to alter the rate 1.5 reduction in sampling rate, so on and so forth. How can we realize efficient structures, right? This is a question for a rational sampling rate conversion, and if you recall at the very beginning of the multi-rate module, we discussed that some of the basic problems would be sampling rate conversion, right. I mean we would want to go from 32 kilohertz to 48 kilohertz or 44 kilohertz to 48 kilohertz to 44.1 kilohertz and so on and so forth, right. So, if we need these conversion rates that are possibly rational rate conversions, how can we go about doing this? So, now we are now at a stage where we want an efficient structure for realizing these sampling rate conversions. So, let us get started. For doing an m by L decimation without polyphase, we are very inefficient. Why? At any point in time L minus 1 out of L multipliers have 0 inputs, that means we are just filtering these zeros. Second, only 1 out of m output samples is being retained. I think this is very important. These 2 points are really very important for us. What happens in upsampling, what happens in downsampling. Now let us consider an example here. Suppose m equals 3 and L equals 2, right. So we have studied polyphase decomposition, we have studied Nobel identities. Let us see what we can do, right. One may think, of adopting the following architecture using type 1 polyphase decomposition. We use a type 1 polyphase decomposition. We can think of the following structure, right. We have x of n, discrete time signal, we upsample this by 2. Now we have 3 branches. Because it is type 1 polyphase decomposition, we look at it from the decimation filter perspective. So we downsample by 3, feed this to a filter which is E naught of z. There is a delay here. We downsample this by 3, feed this to a filter which is E1 of z, and one more delay path for the last polyphase component. And then we sum all the outputs and we get what we want, and we have accomplished an M by L conversion. This is one structure, call this structure A, and this is exploiting the decimator. Right. If I gave this problem to one of you in the class, do an M by L decimation, probably if you have just studied Nobel identities, polyphase decomposition, this is one realization one of you could provide. Somebody else in the class can still argue, well, why should I exploit just the decimator here, because we also studied what we could do with a type 2 polyphase decomposition for the interpolation filter, right, and we will exploit it from the interpolation filter perspective, right. So let us do that exercise. So you could start with the signal x of n, you filter this through R naught of z, this is followed by upsampling by 2, there is a delay, then you have R1 of z, another upsampler here, followed by downsampling by 3 and then y of n. I call this structure B. This is by exploiting the interpolator. Now, one of you may question if structure B is efficient or structure A is efficient, and realize the possibility that both of these are still inefficient, because in structure A you are upsampling by 2 here, that means you are inserting an additional 0 that goes through this filtering process here, which is not efficient, right, because we said these two things make an M by L decimation inefficient, because you have not exploited the polyphase at the interpolation side here, at the expansion side, followed by some filtering here. Similarly, one can argue that, well, though you exploited the interpolator here by efficient realization, you are failing here from the decimation perspective, because anyway you are throwing away 2 samples when you are downsampling by 3. Now, can we combine, the question that one has to ask is, can we exploit both A and B to take full advantage of decimator and expander? Right, this is something interesting at this point to ponder about. Are we at the dead end, right? I mean, I did expansion, decimator, I mean polyphase realization for expansion with filtering, then decimation, and the other way around. Are we at a dead end here? So this is an important question, right? When we discussed in the very beginning of the multi-rate signal processing module, looking at a conversion rate from 32 kilohertz to 48 or 48 to 32, 3 by 2 decimation is happening, right? From 48, if I want to reduce it to 32, it is 1.5 times reduction. That is exactly the same problem here, a practical problem. So this question was addressed by a gentleman by name Shao way back in 1990, and that led into a really truly efficient architecture for an M/L decimator, okay. And this is very simple, as you can see, with a few elementary tricks we can just get to the answer. So we adopt a technique by Shao way back in 1990. It is published in the transactions, IEEE transactions, and this gives us an efficient architecture for an M/L conversion. So the trick, I think, is important, what the trick is. So if you think about a delay, right, this delay z power minus 1 can be written as z power minus 3 times z square. No big deal if you just say, what is a big deal if I say, if I write z power minus 1 as z power minus 3 and z power z square. But observe the powers 3 and 2 that are appearing here, and carefully think about the m equals 3 and l equals 2 and see what you could do, right. So if you, we will see how this trick is useful, right. Let us start with this step. We will start with type 2 decomposition at the interpolation stage. We have R naught of z followed by an upsampler, then we have R1 of z followed by an upsampler, and here we had a delay element, right. we had a delay element, and this delay element we will write it as z power minus 3 here. At this branch we will say z square, and this is this unit delay z power minus 1 followed by downsampling by 3. Right? So this is the first step. The next step is by pushing this downsampler into each of the branches as what we have usually done, and then now think about applying Nobel identities to this path. So let us now, this is the first step, right. Next what we do is we push the downsampler into the branches before. So therefore, this would go in here as well as here. Okay. And what we would do is we will use the following identities. Z power minus 3 followed by downsampling by 3. This is just like Nobel identities, right. We can write this as downsampling by 3 followed by a delay, and then we have an upsampler by 2 followed by z square to be equivalent to an advancement which is z followed by an upsampling by 2. So this will simplify things a little bit. Okay. So what we do is the following. So we have now x of n so I just write this z here, r naught z upsample by 2, downsample by 3, a delay followed by r1 of z upsample by 2 and then downsample by 3. So you might be wondering where did the z appear, right. If you apply this Nobel identity, right. So you have at this point you have upsampling by 2 followed by z square. We replace this by z with upsampling by 2. Now this is like a cascade of R naught of z and z. You can just exchange the cascade, right. You can say R naught of z times z is basically z times R naught of z, and that is what is happening here. Now this seems to be good. We have done some simplification, but we are not yet there. If you can sort of realize, so because we have R naught of z and R1 of z, and then we have these upsamplers followed by downsamplers. Now there is another trick we could invoke, which is from the interconnecting systems. Notice that you have L equals 2 and M equals 3, the GCD of L and M is 1, so you can basically exchange them. Okay. So the next step is to realize that we can interchange the decimator and the expander, since GCD of 3 and 2 is 1. Okay, we do that, and what we get is x of n. The rest is all the same. We are downsampling by 3, upsampling by 2. We have a delay element, R1 of z, upsample by 2. So this is downsample by this is down sample by 3 followed by upsampling by 2, and we just exchanged the 2, we just swapped these two. Now what we have to do is, now these filters R0 and R1, though they are polyphase filters obtained from interpolation, we can do a type 1 polyphase decomposition on these filters further, because this is basically filtering followed by decimation. We will do a type 1 polyphase decomposition over R0 and R1 further. So let us do a type 1 polyphase decomposition on components R0 of z and R1 of z. So if we did this, say R0 of z can be written as some R0 naught z cube plus z power minus 1 R0 1 of z cube plus 2 delay elements R0 2 z cube, and we have R1 of z is R10 z cube delay with R11 of z cube plus 2 delays R12 of z cube. Okay, and then we will sketch this. So basically we have x of n we have a z here. So we have downsample by 3. So basically then you apply Nobel identities, right? You plug the polyphase representation, then apply Nobel identities. I get R naught naught of z delay downsample by 3 R naught 1 of z, then one more delay downsample by 3 followed by filtering with this filter R naught 2 of z, and then I combine all of these components together, and then I upsample by 2 followed by a delay, right? And then similarly we have one more branch, and from which we have to realize something similar to what we did. So we have downsample by 3 followed by this filter R10 of z, first branch, then we have a delay. So I think I would just erase some of these blocks here. Just to get this diagram a little symmetric. Followed by downsampling by 3 with R11 of z, and then one more delay element here, downsample by 3, filter this through R12 of z. Now we combine all of these, upsample this by 2, and then sum this up at this point, right? And this is an efficient realization because we started off with a type 2 decomposition from the interpolation side, and then we did a type 1 decomposition exploiting the decimation side, and then we have really basically we are very efficient. We are not throwing away samples as a part of the decimation process, right? We are not wasting our efficiency on that, and then similarly we are not just filtering these zeros because we started off with an efficient realization for interpolation in the very first step, right? And this is an efficient architecture for fractional sampling rate conversion. I mean, you could decimate, you could reduce the rate by 1.5, you could increase the rate by 1.5, you could do any rational sampling rate conversion. I mean, here I mentioned this as a fractional sampling rate because again we are doing an m by l, we are doing a reduction by 1.5 times. Okay, so this is sort of the goal, and we have applied all the tricks that we could think of. We did polyphase decomposition, we then applied Nobel identities, we looked at interconnecting systems, we did both type 1 and type 2. So, all the tricks that we learned as identities we have basically taken care of in this architecture. Now, we can imagine why this GCD has to be, why this GCD is important, right, and if we want a nearest M and L parameters such that the GCD of M comma L equals 1. So, if you think about 48 kilohertz and 44.1 kilohertz, look at the ratio 480 by 441 and reduce this to the nearest rate that you, nearest M by L rates that you want, okay, and then you can go about realization of efficient architectures for this. So, I think this is a very important first step, and then if you now we did not think about how we could exploit the base filter itself. I mean, I leave this as a homework exercise. Suppose I give you a base filter which is an FIR filter and that has a symmetric impulse response. Now, take that property into account and then see how these polyphase filters could be more efficiently constructed, right. I mean, how you could do better filtering operations with these filters. Yeah, at this point you might just wonder about one little detail, which is you have this element which is basically Z, which is an anticipation element. It is not a delay, right, it is an anticipation element, and one may wonder how can you realize this in practice, and it is not too difficult to think about it. I mean, what is this delay, this anticipation element telling us? That means we need to look at one sample in the future, right. I mean, this architecture would seem futile if you were thinking about serial communication where you are sending one sample at a time for processing, and there you really cannot anticipate anything, right, because everything is the present or whatever you have in the past. But if you buffer the samples by some number of samples initially, then you can point to a particular location in your buffer. I mean, you can always basically get over this anticipation because since you are buffered, you already have some samples at one shot. So, therefore, you can really realize this advancement by figuring out what that sample has to be, and I think post that everything would be basically pipelined and the whole architecture can be very efficiently realized in hardware. So, this is a little bit of detail. I think a little bit of thought from your side can make you realize and understand that this is indeed a very practical architecture. By just buffering you can realize everything to work as is. Okay. Okay, I think with this we are done with this lecture.